Okay. Yes, I'm Keith. That's me. Another picture of me. I guess I provided that picture. It's so pixelated, it's my fault, so, you know. Okay. I will hope to get this in 25 minutes. We'll see. All right, which button do I hit? This one. Oh, okay. That's kind of a restatement. Yeah, okay. Who am I? I'm a mathematician by training. That's what I know how to do best. It's what I love. I wish I was still in mathematics, really. But I'm in ML and AI because I believe that this is where I need to be on the intellectual front line. You know, even if I was proving twin primes, like, okay, who cares? So, you know, when I made that decision, I was like, man, I don't know how to program at all. So I came to Google as a SWE. Eventually I moved to RS because that's kind of like my natural home. RS is research scientist. SWE, I think you all know, probably. I still, to this day, am a pretty pure scientist and researcher. You know, like I would be an academic in a different life, or you know, in a different environment. If we were in the 50s and it was quantum chromodynamics still, that's what I'd be doing. But I think that's kind of the analog of this is what that is then. Everything I'm about to say is my own opinion. This is not speaking for a GDM in any way. Okay, so what do I work on? Primarily, I think about what will the next gen learning systems that we're building, okay, I'm at a big lab, so you know, this is all like sustaining technology stuff, not like disruptive really. What are they gonna need? Particularly from the perspective of systems and algorithms. You know, since I kind of have this like really cross-stack background, like way abstract in math and way down low in SWE, I was in compiler stuff. I try to leverage that and think across the stack. Okay, so first half of this talk is gonna be about what are they gonna need? What are they gonna need? You know, you gotta know what they're like now. So okay, what are they like now? The first thing we all know is that they're big. They are giant. Okay, so how big? All right, this is all public data, right? I'm not trying to leak anything from the way Gemini's trained. Grok 3 was supposed to be whatever, 10 to the 26 flops. The top 500 #1 supercomputer is down the peninsula down there. Gets about 2 times 10 to the 18th flops through a second. So this would have been about 6 years if you trained it on like traditional HPC hardware. So that's a long time. That's as long as it took to go from GPT-2 to what we have now. So you're not gonna do that. Okay, how quickly is this growing? Again, public data. Grok 2 to Grok 3 was 10x in 6 months. That's a bit of a weird fake number because it's like kind of a catch-up thing. But we can anchor in Claude. Claude is about maybe 5x in about a year. Okay, this graph that I had, you know, one of my great use cases for these tools right now is graphs, because I hate making graphs. So I'm just like, please, Gemini, give me a graph for this thing. This is whatever, Moore's law against 5x year over year, log scale. So that's a big gap between those two. So how can we sustain that? There's only 2 things that we really know how to do to sustain this thing. One is specialize and one is distribute. Okay, before we even get there, is it all gonna stop? Is it all gonna blow up? I don't know, maybe, possibly. Can the Earth support it? I mean, I think so. You know, this is all traditional batch processing stuff at the end of the day. So, you know, you gotta build your power and yeah, that's hard. I put a little shout out to the infamous PyTorch power plant no blow up equals 1 flag that's in some code base somewhere. This is like 6th hand, so you know, this is apocryphal. Who knows if this is true? But basically, my understanding is that it just like runs fake work when instead of waiting, because if you have these giant spiky power draws, that's apparently a problem. Will the data be there? That's a big question, but I've put a few reasons here to believe that the data will be there. RL and more generally learning from experience, you know, we're all kind of talking about that. Now everybody's trying to, you know, get themselves away from the bootstrapping need of like tokens from the internet. But there's also a lot of untapped data sources out there. I think that the deep web is, I don't know, 100x bigger than the quote unquote shallow web that we index. Okay, how are we gonna access that? Who knows? There's also giant incentives to make more data. I think it's not a secret that every frontier lab is trying to do synthetic data well. Everybody's trying it, so somebody will probably crack it. I have a hard time believing that none of these 4 things are gonna line up and data probably will, in my bet, it will not be the thing that stops us. There's kind of a deeper question, which I think is worth asking, which is there any reason to keep doing it? Or are we all just making AI slop? Or are we like, whatever, just brain rotting everybody in Gen Z and Gen Alpha? Is that the like TLDR of what we're doing? I mean, I'm gonna go back to like my background. I'm a mathematician and a scientist, so like that's why I got into computing, was I thought this would be the scientific front line. I still think so. I don't think I'm alone in thinking that, you know, this is gonna be a foundational technology to enable us to make much bigger progress in math and science than we've ever been able to do before. That's why I got into it, and I don't see any reason to believe that that's not true. Okay, and like whatever, I'm a classical optimist, so that's enough for me. So let's assume we're gonna try to make it work. Okay, this is where I'm gonna present like what is my kind of perspective on why do I think that focusing on distributed stuff from the algorithm systems angle is the most interesting problem in optimization for the next probably decade. We're gonna make it work by thinking distributed first. Okay, so we gotta go back. We talked about specialization and distribution. We gotta touch on specialization for 1 second, even though I'm far from an expert here. This obviously is right as the GPU and the CPU, right? We talked about how like traditional HPC is not gonna get you the throughput you need, so you gotta specialize your chips. Not really a way around that. People are trying to go whatever, do crazier specialization in this too, right? Like bake transformer architecture in, bake weights into circuits and stuff like that. So yeah, this is like one of the main thrusts of how we're gonna do this thing. Okay, but let's just talk about GPU and TPU. How quickly is their throughput growing? Again, this is public data, estimated to be 1.5x a year for fixed precision, stable since about 2020. This is faster than Moore's Law, right? Because it's 2.25x every other year, right? Am I squaring that correctly? Sounds right. Okay, whatever. Square that number, it's bigger than 2, because 1.4 is what, square root of 2, right? That's the mathematician talking, I guess. You can get a 10x perf boost from the quant we kind of like roughly know how to do, FB32 to int8. Let's assume you can get another 10x by just like, you know, general category of more quantization. So that's 3 years of the runway that we need. 5x, 5 to the third is 125, right? So this is approximately 3x, or approximately 3 years of the runway we need, maybe, more or less, depending on how you kind of measure the throughput growth. Okay, this tells us that we need to distribute 1, and 2, we will need to distribute more as time goes on. There's like no way around this in the way we're doing it, assuming that everything's gonna continue in the way it is. We're not all just gonna, whatever, go home and move to Costa Rica and be done working, which, you know, any day now I might do that. Okay, so we gotta distribute. This is not a secret because we all distribute today. And there's a lot of ways that we do it, but I will argue that it really follows kind of one core paradigm, which is take a program that we're very familiar with, which is computed derivative, and scale it up. This is what has led to the many kinds of parallelism we have today, which is in order here: tensor parallelism, sequence parallelism, expert parallelism, pipeline parallelism, fully sharded data parallelism, and normal data parallelism. Okay, in an earlier version of this slide, I had like a TLDR description of all of these, but then I was like, no one's gonna read this, so whatever. Trust me that there's a lot of ways to partition this program, and that a lot of people do a lot of work on this. You know, whatever. People do dual pipe, and people do crazy things to schedule their micro batches and blah, 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 to do all this optimization to make this distribution as good as it can be. Okay, but these are all about partitioning compute in this one paradigm to keep it all going. I think that this image is like, by the way, completely wrong. I can't remember if there was, obviously these are all generated, right? So like, I think there's some bug in there that I noticed, and I was like, okay, whatever. No one's gonna read it that closely, so just trust me that this is all fine. Okay, another paradigm we can follow is to, instead of anchoring in the program, anchor in the scaling. So like, when we scale, it's hard, yes. And it's hard to predict, and this is a lot of people's jobs. A lot of people make a lot of money because they're very good at controlling the scaling process in the one paradigm that we're following now. But at the same time, certain things become free, and we should be thinking about these things first. I'm gonna argue that as a research community, I mean, again, I'm a scientist and mathematician at my heart, so like, I think about whatever. We're all part of this giant community. We're trying to make this thing work. I'm not a great capitalist, I guess. As a research community, we have not yet effectively leveraged this freedom. Okay. So again, TLDR of this is that my claim is that designing algorithms and methods which are intended, first and foremost, for this setting, keep scaling it, keep distributing it, is the most interesting problem in optimization ML algorithms for the foreseeable future, and a lot can be done here. Okay, that's my basic claim. The rest of this talk, time check. Oh, about 10 minutes, right? Is that right? Any organizer? Great, I'm doing great, man. I really thought I'd definitely run over. The rest of this talk is gonna be about one example of following this paradigm. I really don't believe that we've cracked this paradigm. I don't think this is the only thing you can do. I think there's much more you can do, but there is an example that shows us that there is something here. There's a there that can work. Okay, so what do I mean distributed first? You know, because I kind of do this cross-stack stuff, I think of it primarily as like surfacing to the algorithm developer and programmer some systems features that are relevant for them. So it takes art to know what's relevant, right? And what's relevant might change. And it's very hard to predict what's gonna be relevant in a year. From personal experience, people have predicted things that are gonna be relevant in a year for the scaling problem that are completely wrong. So people that are very good have made those predictions, and it's a very hard thing. So okay, when you're in that kind of position, you have to look for principles. MapReduce and things like Flume and stuff, like big distributed data flow stuff, is one kind of set of principles that you can anchor in. So this is kind of where I started in this journey. I started working on enabling the dead simplest, most simple you can imagine, pure synchronous SPMD, single program, multiple data. So like you write there's only one program, there's a bunch of inputs, right? Okay, that's the way that GSPMD works. From Google, right, we call everything G something. So GSPMD is whatever, Google version of SPMD, like this. That's how XLA does things, TPU does things. But programming in this way, kind of MapReduce way, give me a function, I'm gonna map it across some arbitrary axis and spit you the results back. Through the JAX XLA TPU stack is in fact non-trivial. Shockingly so. When I started this project, I was like, yeah, it's gonna be whatever, like a week or something, right? It's just like a pure library. And it kind of is now, but we needed a lot of changes down the stack. Sort of, this is my project about 2 years ago to a year ago, more or less. Dr. JAX for differential MapReduce primitive in JAX. We almost called it Marx MapReduce primitive in JAX, M-A-R-X. But we thought that would not fly, so, so we didn't. Dr. JAX is much less controversial. Okay, but what's the programmer gonna do with it? I was coming at it from kind of the bottom of like, well, we need to enable certain kinds of things. We haven't pursued this path because certain things are just too hard, so no one does them, right? Okay, so there's an independent group of people at GDM who were kind of trying to do something similar, which was effectively like precisely control the reduction that happens between your data parallel workers. This first example was just like don't reduce every step, basically. Actually, my background is from federated learning, so like this is all kind of algorithmically, exactly algorithms that were coming out of federated learning, like 2017, even earlier maybe. Well, like arguably there was one real innovation from FL in 2017, and that's like all we've ever done from the algorithmic perspective. Okay, but this is exactly an example of what I mean. We use the existing tensor replication, something from the system that's usually hidden from us, to do something interesting. So okay, these people were working on this, we moved them on top of Dr. JAX, and we started working together. Okay, so we had to ask, how interesting? From the systems perspective, quite interesting. At least as interesting in pipelining is my claim. But of course, it's a different program, right? It's not transparent from the ML perspective, so you have to be very careful about whether you care. In the vanilla version, we did the traditional federated style paradigm, unroll a bunch of steps, do 30 steps, and then amortize the cost of the reduction. But this is not great for you because there's really, really spiky network traffic, right? You're not doing anything for 30 steps, which is like, okay, I almost quoted a number. I'm not allowed to quote any numbers, so stop myself. 30 steps, some amount of time. And then you're blocking and everybody's syncing up. Yeah, you quote unquote amortize it, but this is a big problem for your system. Okay, so the obvious thing to do is to split the synchronization into fragments, like split your model up into 30 pieces and sync a piece every step instead. This we call the streaming version. This was a paper was out earlier this year. And we also noticed in the same setting, so when you do all these steps and you sync everything up, this is actually worse for you than doing distributed data parallel if you can fit the overlap of the DDP synchronization inside of the step, like as the backwards pass is happening, because we would need to ship everything after we take the step, so we need literally everybody to block. But in this setting, when you split the model up like this, you can actually delay shipping the fragment across until the next step. The biggest thing you're going to lose there is the fragments compute for that step. So if you have like 30 fragments, right, that's like 3% or something. So that's a lot better than some large percentage because you are waiting for your gradients to come across the wire for a long time. And you're never waiting as long as you can get 1/h of the model over in a step time. So that's a giant, enormous reduction in bandwidth. We'll talk about it later. It's about a factor of 100 required bandwidth you need. Okay, but you can obviously pin all your chips if you don't care about the utility of the program you're executing. You just like, whatever, run a bunch of matmols. It's like, yeah, you don't need to sync anything ever. So you can pin all your chips if you never care about the program you're running. So you have to ask, like, this is where the real cross-stack stuff comes in. You have to actually ask this from the ML perspective. Can you use this well? And we showed in this paper that yes, actually you could. You can train models to the same quality as baseline data parallel training with approximately 100x lower required bandwidth to achieve high utilization. And this has been replicated at least a couple times. This I stole from Primentilic folks who I know are around. Maybe they're not here, but I stole this picture from them. So this has been replicated at least once by them. We've done it like 4 or 5 times in different models and code bases. I think another paper just came out that also replicated this. So yes, this is definitely, as far as we can tell, as many times as we've tested it, it is real. Okay, TLDR, there is one thing that's interesting here, which is that if you want to do DDP training, you could train something to the same quality while cutting your bandwidth requirement by 2 orders of magnitude. Do we really care about this? You know, me being from a big lab, I'm thinking about this from the perspective of a sustaining technology. So it's like whatever the paradigm we currently use, and we just are trying to keep going with it. A lot of the folks here think about it more from the disruptive angle, like how can we make a disruptive market around whatever, some new piece of technology. I don't think about that at all. I'm not paid to think about that, but I hope somebody thinks about it seriously. From this perspective, this only matters if it can scale. How does it scale? This is another paper about to, well, it's already public, right? But it's about to be in NeurIPS this year. So we really asked the scaling question very seriously. We learned a couple of things. More, splitting the compute up further scales better than splitting up less far. We can single shot extrapolate everything. And in fact, our performance was actually better than the data parallel baseline. This is a truly different algorithm. It is truly better in some real sense. There's increased horizontal scalability, which is maybe not shocking. So if you are training beyond your critical batch size, which is typical ML thing, right? It's like you scale your batch size. I got 2 minutes? Oh man, all right. I'm gonna have to rush through this now. Okay, whatever. If your batch sizes are big enough, you may already be in a regime where like very decoupled training is actually just strictly better for you. The tuning is not too crazy. So you can fix essentially all of the like outer synchronization stuff you need to do across scale. And as long as you get the inner scaling right, the normal scaling right, everything's good. Okay, so there's some algorithm here. What's next? Again, this was only one example. I really don't think this is the best we can do that can be done. We leverage a systems feature that's already present. We show that this kind of systems feature can be leveraged at a minimum for systems reasons. I personally think for ML reasons too. But arguably, more importantly, yeah, we show that this can actually work from the ML perspective. You can get strict gains from the ML perspective by leveraging this kind of thing. This is what I mean by saying distributed first. Creating the disruptive market is extremely hard. As I mentioned, I'm at a big lab. I'm not going to do this, right? Like, you know, nobody's asking me to like, I don't know, figure out how to incentivize all the actors correctly so that this works. No one's asked me to do that. I'm not thinking about that at all. People here are the people who will do it. What I hope the role that some of the big labs can play is to show that there actually is a lot of room to play with, even when you do this like really, really rigorously from the scientific perspective. So I hope to have convinced somebody that with the right disruptive market, there's going to be a lot of room to run by decoupling training further than we do today. That's it. Man, I hit it.
You did it, Keith. Yeah. Big round of applause.
Great.
That was awesome.
Thank you.